topic is battery thermal management system for electric vehicle. So the electric vehicle face the thermal problem in a battery. So it is a major problem in a EV. So myself, Indhumathi, Assistant Professor, Department of Electrical and Electronics Engineering, PSNCET College of Engineering and Technology. So first of all, what are the content are here? So first we discussed about background, then primary and secondary cell. These are the basic, and then electromotive force and backup time of battery, then types of battery, then point to ensure during the BTMS and types of BTMS. So the BTMS in the sense of battery thermal management system. So first of all, the battery overview. We already know there are two terminals, one is cathode, another one is anode. So the cathode terminal, the chemical reduction is occur, and the anode terminal, the chemical oxidation is occur. So in between of anode and cathode, we have electrolytes. It enables the flow of electric current by transporting ion between anode and cathode during charging and discharging. So these are happening during the charging and discharging. Then primary cell. So there are two types of cells, one is primary and another one is secondary. So the primary cell is single time use and there are no fluid in the cells, hence it is also called dry cell. So non-rechargeable and non-reversible chemical reaction and low discharge rate. So this is a primary cell, and this is applied in single time use means clock, in a remote, so etc. Secondary cell. So this is, it can be charged and recharged process is available and reversible chemical reaction, and these are made up of wet cell, that is liquid electrolyte, and molten salts, that is high temperature liquid salts. So the secondary cell is mainly used in EV, that is lithium ion battery, lead acid battery, nickel cadmium battery, so on. So the electromotive force. So the electromotive force is happening in a battery, that is EMF, that represent the maximum potential difference across the terminal. So there is no current flow, that is open circuit voltage. It is driving force that moves charge through a circuit. If a battery supply watt joule energy to Q coulombs of charge, EMF is calculated. EMF epsilon is equal to change of joule divided by change of charge. So a battery supply 15 joule of energy to 5C of charge, the EMF is 3 volt. So this is the calculation of EMF. Then charging and discharging. So during charging, when cell is during discharging, it's lost EMF. That means it provides the EMF to the load. The terminal voltage is given as V is equal to epsilon minus IR. Epsilon means EMF and the IR means internal resistance. R means internal resistance, I means current. During charging, it acts load, hence terminal voltage V is equal to E plus IR. So battery capacity. So battery capacity is defined as the measure of a battery ability to store or deliver the electrical energy. Okay, so it expresses ampere hour or watt hour. So it depends on factors such as quantity of active material, battery design, operational conditions and discharge rate. So backup time, battery capacity divided by total load. So ampere hour into volt divided by total load means watts. So this is the backup time calculations. Connecting batteries in series. So connecting batteries in series in the sense, we have to add the voltage. A set of batteries is said to be connected in series when the positive terminal is one cell is connected to negative terminal of the successive cell. So this is adding the voltage. Wiring batteries in series provided a higher energy voltage resulting in a lower system current. Low current indicates that you can use thinner wiring and suffer less voltage drop in the system. So development of battery pack. So that is electrical design, mechanical design, battery management system, thermal design. So mainly we consider the thermal design because of due to thermal so many risks are happening. So that's why we are more concentrate about thermal design. So types of battery. So the types of battery in the under of secondary cells: lithium ion battery, lead acid battery, nickel cadmium battery, nickel metal hydride battery, and solid state battery. So first, lithium ion battery. In lithium ion battery is the most common battery that found in electric vehicles, right? So because of its high energy to unit mass, it is chosen as the EV. And also they are light in weight and they have low self-discharge level. So there are three types of lithium ion batteries: prismatic battery, pouch battery, cylindrical battery. Lead acid battery, it was used as a EV vehicle battery till 80s. So after 80s we are move on lithium ion battery and other batteries. Lead acid batteries are heavier and have a low energy density compared to lithium ion batteries. So nickel cadmium battery, it has exceptional energy density and high efficiency but low cycle life. Despite its superior properties, it is not preferred for modern electric vehicle. Yes, they are used as EV car batteries during the 90s but were soon burned because of their toxicity. So nickel cadmium is very toxicity in our environment and in our human also. So they can stop in a car. So nowadays we are using the lithium ion batteries, and as well as the manufacturing is also expensive. So which are made up of researchers look into alternative. Nickel metal hydride battery. So its charging capacity is 2 to 3 times than the lithium ion battery, and it is extended life cycle up to 40 times nickel cadmium batteries. So it is charged only by regenerative braking mechanism. The regenerative braking mechanism converts some kinetic energy to heat while applying brakes, and its recovered heat is used to charge the battery. NIMH batteries have a high self-discharge rate, yet they are used in hybrid vehicles as the probability of explosion is relatively low. NIMH batteries are cheaper than lithium ion batteries. Okay. So now we are entering into the topic BTMS. Why BTMS is important? Okay. So first of all, battery lifetime and performance depending upon the operating temperature. So the operating temperature is decide the battery lifetime and performance. So higher temperature of battery increase the capacity but decrease the lifetime. Okay. So if I increase the temperature, the capacity will increase but lifetime will decrease. Look at the graph. Batteries generate heat due to electrochemical reaction, which will increase the temperature of the battery. When the temperature exceeds the allowable upper limit, it affects the life of the batteries and cause the battery to short circuit and explode. So it leads to short circuit and explode. At lower temperature, thermal reaction required to generate energy become slower. So challenges. So the optimal temperature in between 15 degree to 35 degree, below 15 degree Celsius is also affect the battery performance, and above 35 degrees also affect the battery performance due to increased resistance and intensified side reaction. So any failure in single cell can affect the overall capacity of the series. Temperature variation from module to module within a pack can lead to electrical imbalance which affect battery pack performance. So the battery thermal management, okay, because of the thermal is very severe to the battery, so how it will manage, how it will regulate, okay. So they regulate the temperature of battery pack to ensure optimal performance, safety and longevity. So the battery maintain the temperature is 15 to 35 degree, it is a preferable range. So the BTMS mitigate degradation and preventing thermal runaway through, so the methods are active cooling method, passive cooling method and hybrid cooling method. So there are three methods to cool the batteries. So effectiveness, why the BTMS? The BTMS ensures sufficient cooling and heating capacity. So we ensure, then it should be, the energy consumption should be minimal and simple design so that it is easy to manufacture and affordable. So we already told the cooling, active cooling, passive cooling and hybrid. So there are three types of coolings. I mentioned the three types: liquid, air cooling and PCM. The PCM means phase change material. So liquid means immersion or direct cooling. Immersion cooling means the battery directly dip into the water. That is immersion cooling. And indirect, cold plate, jacket and heat pipe. So these are all water fluid through the pipe to the battery. So this is later we see. Air cooling, natural convection, forced convection. The two types of convections are there. So optimization techniques, battery layout, airflow channel layout, cooling fan placement operations. And PCM, transition phase, material decomposition. So solid to liquid, solid to vapor and liquid to vapor. So these are all the transitions happening in the phase change materials, and organic, inorganic and aerotic materials composition is used in the PCM. So first we see the air cooling. So the air cooling is mediumly we used in a battery. Rarely we used in a battery in EV. So it is divided into active and passive heat dissipation method. So it is divided into natural convection, forced convection according to cause of airflow outside the battery pack. So natural airflow convection, air is supplied to the battery pack naturally through the convection without using extra energy in BTMS with the natural airflow convection. So forced convection achieved via the specialized energy consuming mechanism that forces air into the battery pack around the batteries. So what is the difference of natural and forced means? Natural, there is no external energy, and forced, we have external energy to force the air. So the air-based BTMS are mostly for battery packs with mild cooling demands. So this is active cooling, outside air or cabin air directly front to the battery. Passive cooling, we just evaporate and radiator to outlets. Advantages: the structure is simple and quality is relatively small. So there is no possibility of liquid leakage. Effective ventilation with when harmful gases are generated. The cost is lower. Liquid cooling. Next method is liquid cooling. So first the type is immersion fluid. So I already told the battery is directly dip into the liquid. So that is immersion cooling. So in this way the battery is perfectly sealed by a aluminium shell and then dip into the immersion fluid. So this is some way it is very dangerous because of it may possible to liquid enter into the battery and then the perfect supply is not given to the load. So liquid cooling, next liquid cooling has been extensively used in the EV market because of its high specific heat and thermal conductivity compared to the air. So the liquid used is glycol and water is usually mixture of ethylene. Liquid cooling can be divided into direct contact and indirect contact. So direct liquid cooling, so that is I already told. So the static flow, forced flow and static flow, forced flow in a complete immersion, partial immersion. Okay, so the direct contact types of to immerse the battery into the cooling liquid. The heat exchange effect is excellent and temperature uniformity is good. The disadvantages is that it put forward a high echo moment on the ceiling and the insulation's performance of the inside and outside of the battery pack. Indirect liquid. Next we move on to indirect liquid. So using any geometry, okay, that is the coolant, the liquid is passed through the channel and then the battery will be cooled. So a cold plate serves as the critical interface within a liquid cooling system, guiding pumped fluid to heat sources and transferring waste heat into coolant for subsequent cooling. So cold plate features a heat source mounting surface, internal passages for liquid to pass through, and the inlet and outlet. So phase change material is put into the battery pack. So next one is phase change materials, and it is used to latent heat to absorb the heat generated when the battery is discharged. Its advantages are simple structure and temperature uniformity. Disadvantages: volume and mass of the required phase PCM are large, which reduce the overall efficiency of the battery. That is also its overall density of the battery. So next, the problem is coupling with the low thermal conductivity of the PCM. So if it is low thermal, it is not a good conductor to conduct the heat. Continuous battery heat load after completion of PCM, leakage of PCM, volume change, and inhomogeneity of the whole module is repeated melting solidifying process. So advantages: passive and silent. Unlike fans or pumps, PCM operates silently and do not require external power. Thermal runaway production. PCM help prevent heat propagation from a single faulty cell to neighboring cell. So hybrid cooling. So hybrid cooling means it's a combination of two cooling methods or three cooling methods or two or more cooling methods. So now we use the PCM, liquid cold plates, air cooling. So the combination of the multiple methods combines the hybrid battery cooling to enhance thermal management, improving efficiency by over 20% and temperature uniformity by up to 56% compared to, for example, air only systems. So air and liquid is a hybrid. So one vehicle, it is inbuilt by air cooling and liquid cooling. So the air, this is the symbolic representation of the the air and liquid cooling. So through the air ventilation, the air is inlet through the battery, and under the battery we just pass the water and it will pass through radiator, then again it will be again and again happen. The air is outlet through the existing of the car. Liquid and phase change materials. So the square shape is battery. The square shape is battery, and this is liquid passing coolant channel, and this one is phase change materials around the battery. The yellow is the battery. Okay, so these are all the way to connect the phase change materials and liquid. So drawbacks, PTMS drawbacks: less experiments on actual battery packs under the actual EV running condition. Pumping power studies in BTMS are rare in spite of being the important condition practical application, because of some researchers only researching the heater. The heater is simulation of a battery. So considering constant heat flux as heat source instead of real battery with the actual power values. Okay, so real battery has advantages because of investigator can directly target cooling of hot spot instead of utilizing extra coolant for cooling the entire surface. Majority of PTMS investigations deal with single BTMS techniques instead of hybrid analysis. Considering single temperature of the mainstream flow, but the HEV operate in different weather conditions due to which the performance of embankment cooling with effect. Non-uniform cooling of battery as the bottom portion of the battery remains uncooled, so the top portions get extra cooled. That's why if it is hybrid, that is no problem. Future scope: apply hybrid BTMS to solid state and lithium sulfur batteries. PCM of optimization: explore high conductivity, eco-friendly and fast acting PCM materials. System scalability: extend to multi-cell pack and EV scale module addresses inter-cell thermal gradient. Smart control integrations: use real-time cooling control and predictive algorithm for enhanced safety. Cost analysis: assess economic viability for large-scale deployment. Experimental validation: the test system reliability under real world conditions, temperature variation. Adaptive BTMS for energy storage in solar and wind system. Safety, align with the regulatory standard, propose safety improvements. Hybrid, explore combination with the air cooling, nanofluid or other hybrid enhancement. So next we are move on challenges in lithium-ion battery storage and thermal heat management. So why electrification using battery storage? Worldwide effort of decarbonization to reduce greenhouse gas emissions and addresses global warming challenges. That's why we move on the battery storage. All the form of transportation vehicle and power generation systems are major emitters of greenhouse gases and pollutants. In addition, the search of clean and green propulsion system has been gained a new momentum due to increased demand and cost of imported oil and steady state oil and meat increasingly higher emission standard. Battery classification and types. One of the oldest and very common form of rechargeable and wet type is lead acid battery. Alternative chemistry have given way to new rechargeable battery cell like lithium ion, nickel cadmium and nickel metal hydride. So lithium, we already seen lithium metal anode provide the highest theoretical voltage, rarely used as metal electrode as it is highly unstable. So lithium ion is being used as intercalation materials in porous carbon structure as in anode electrode and other metal oxide structure as in cathode electrode. So battery performance. So the lead acid battery, nickel metal hydride and lithium ion battery. The comparison is here. So the voltage is one single cell voltage is in lead acid battery 1.39 and nickel metal hydride 1.35 and lithium ion is 4.1 up to 4.1. So it is better than the other and specific energy. So 10 to 50 watt hour per kilogram and 60 to 120 watt hour per kilogram and this lithium ion 100 to 300 watt hour per kilogram. Energy efficiency 70 to 85 percentage and 70 to 80 percentage and 95 to 98 percentage. Volume energy density watt hour per liter 60 to 200, 140 to 300 and 250 to 730. And cycle life in lead acid 200 to 400 but lithium ion 3000 to 5000 cycles it may be run. So comparatively lithium ion is better than the other batteries. So the lithium ion battery it will be new consumer electronics because of their high energy density and preferred in many EVs and HEVs because they are high energy density compared to other kind of battery in the market. The specific energy density of lithium ion batteries range from is almost double than that of nickel metal hydride or nickel cadmium batteries. The higher limit of operating voltage of lithium ion batteries is 3.7 to 4.1 volt, which is much higher than other batteries. Why electric battery storage? It is already, you already know, electric battery storage is one of the key player of clean energy technologies due to their high efficiency, high energy density and zero emissions. Considered as one of the next generation of disruptive energy technologies for the power industry. Lower cost of electric storage is transforming the power generation landscape. Extensive development effort or lithium ion battery system for EVs over the last 30 years worldwide. Storage prices are dropping at a faster rate due to the growing demand in the EVs, grid storage applications and demand for integration with renewable energy power generation. So integration of renewable power generation and electric battery storage. Stationary battery storage, strongest market for solar PV panels and wind turbines form energy generation. Integrated small scale PV panels home battery system. Power home during the evening and during power shortage hour. So electric grid storage by utility power plant and delivering during the peak hour. Lithium ion battery dominated the home battery market. So these are the diagram of the electric vehicle and hybrid electric vehicle. So electric motor acts as a generator when slowing down, convert high energy to electric vehicle. Electric energy is generated stored in the battery and later use. Lithium ion battery storage and demands. Among the existing energy storage technology, lithium-ion batteries have unmatched energy density and versatility. So we can store the lithium-ion batteries in up to 5000 cycles. So, and this is high upfront cost and long charging time and cold weather challenges, electricity cost, driving range anxiety, limit of availability of charging points. So in global market for lithium-ion battery, EV battery alone are expected to grow to near 400 billion by year 2035. Continuous increase in global lithium-ion battery and electric vehicles, BEV market is expected to grow and dominate next 2 decades. So other sectors of battery storage and electrification demand. Battery storage of renewable energy, grid storage, data center, fast EV charger, commercial and industrial batteries, and electrification in construction, agriculture, mining, and long overhaul truck, buses and train, and off-highway vehicles. So, what are the challenges means? The increasing material cost, lithium and cobalt, nickel, cadmium, supply chain issues also, and energy source of charging and energy cost, and management through the entire life cycle, raw material extracting and processing, and reuse after primary use, end of the life. So secondary life is this. So requirement, challenges and choice of lithium-ion batteries for EVs. Sufficient capacity for longer range. So that's why we use choice. Fast charging capability and match the drive and duty cycles, and high energy density and sustained performance over the wide range of the high discharge cycle, charge rates and cycle, and environmental condition. Uniformity and isothermal conditions among all cells in a pack. Operate at a safe temperature and avoid thermal runaway. Long cycle life, avoid degradation and aging, reduce cost and meet weight and space restriction. So these are the major challenge. And battery pack design. So we will design the battery and consider the above and around the terms. First we understand the charge time, battery materials, performance and efficiency, capacity and range, safety, flawless and operations, degradation and life, cost, lower weight and volume, supply chain, and E&E condition, that means environment condition. So these are all the design challenges. So battery storage pack. So in a battery, around the battery we use the fire retardants and tin adhesive and active and air and liquid cooling methods. So these are also inbuilt in the battery. It is a battery pack. So battery aging and performance degradation, power and energy of capacity degradation due to increase in internal resistance, results in heat generation, side reaction causing heat generation, loss of active materials. So capacity loss over time due to degradation of the electrodes and electrolytes, due to issues ranging from the formation of highly resistive passivation films, SEA and dendrites formation. So that's all. Thank you.